In this lesson, we're going to learn how to harness the power of a system of equations and use it for a new application that we haven't seen before. We're going to learn how we can use a system of equations to find the solutions to a single equation that we may not otherwise know how to solve. This is an incredibly powerful tool, and so we'll look at a few examples. Our first example will be to give us an idea of how this works. Our second and third example will be to use the process. In the third example, we'll harness the full power of this system. In our first exercise, it says the functions f of x and g of x are graphed to the right. Based on the graph, the solutions to the equation f of x equals g of x are which of the following? I'll tell you right out that the answer is choice C. The solutions to the equation f of x equals g of x are the x values of the point of intersection. Allow me to show you how this works. We see that function f and function g intersect at two separate points. The coordinates of those intersections are 2, -3 and 6, 5. The solutions to the equation f of x equals g of x are those x values. We have two x values, 2 and 6. And so the solutions to the equation f of x equals g of x are simply x equals 2 and x equals 6. Now let's take a look at some examples that will start to get us into the process a little bit deeper. Exercise 2 says to graph f of x and g of x on the set of axes. F of x is the function x squared minus 4x plus 3. We take that function, put it into our graphing calculator, open up the input and output table with Control T, and plot the points on the graph. When we draw the graph, it looks like this. It's a parabola. Our second function, g of x, is a linear function. We have two ways we can graph this. We see that we have a y-intercept at 1 and a slope of 1/2, so we could use that to construct the graph. Or we could take the function, put it into our graphing calculator, and again use the input and output table. The solutions to the equation f of x equals g of x are at the points of intersection. Those points are 1/2, 1.25, and 4, 3. Once again, I'm interested in the x values, 1/2 and 4. So the solutions to the equation f of x equals g of x are x equals 1/2 and x equals 4. It says explain your reasoning. The reasoning is simple. These are the x values where f of x and g of x intersect. Now you're probably asking a good question. It was easy to see the intersection at the point 4, 3. But how did I ever come up with the 1/2, 1.25? Well, the truth of the matter is that I used my graphing calculator. I put both functions in, and I used menu, analyze graph, intersection, just like I did in the previous lesson. I did that for both intersection points. I can see 4, 3 very clearly on the right, and on the left I see the 1/2 or 0.5, 1.25. In reality, if your x and y coordinates are not whole numbers, or integers really, because they can be negative as well, then we're going to have to resort to the graphing calculator to get those trickier points. Exercise 3 is for you to try. Graph the two functions on the set of axes. Identify the intersections, and then state the values of x for which f of x equals g of x. Please pause the video here, take a moment to construct those graphs, identify those points of intersection, and then state the solutions to the equation. Let's see how you did. The first step was to graph the first function, which looks like this. The second step was to graph the second function, which looks like this. We now identify the points of intersection. Those points are 0, 3 and 3, -3. I'm interested in the x values, 0 and 3. So the solutions to the equation f of x equals g of x are x equals 0 and x equals 3. Now it may not seem that this is particularly useful, but now that you know how the process works, we can look at a last example that'll really show you the value. Exercise 4. Max wants to solve the equation x squared plus 8x plus 10 equals x plus 4. The trouble is that Max doesn't know how to solve an equation that looks like this. He's never solved an equation that has both an x squared and an x. He might learn how to do it later algebraically, but right now he doesn't know. So he looks at this equation and decides that he can use a system of equations in order to determine the solutions. He looks at each side of the equation one at a time. On the left-hand side, he has x squared plus 8x plus 10. So he writes that as y equals x squared plus 8x plus 10. Basically, he wrote it as a function. He then looks at the right-hand side of the equation, which is x plus 4. He writes that as a function also. Y equals x plus 4. He's now ready to use a system of equations in order to determine his solutions. So he opens his graphing calculator, he starts a new document, and he adds a graph. And he enters his first equation, x squared, plus 8x plus 10. And it's a parabola that looks like this. He hits tab to enter his second equation, x plus 4, and he gets a linear equation. He then goes and clicks on the graph and hits the delete keys to get rid of the labels. And now he looks for the point of intersection. What Max has basically done is convert his single equation into a system so that he can use the idea of finding the intersection to identify the solutions. And he does that for both sides, and he finds the points of intersection. The points of intersection are -6, -2, and -1, 3. He knows that the x values are the solutions to the equation. So the solutions to the original equation, x squared plus 8x plus 10 equals x plus 4, are x equals -6 and x equals -1. He was able to solve that original equation that he did not have any idea how to solve by creating a system of equations and finding the points of intersection. This is the real value of using a system of equations to solve an equation that you might not know how to solve. This is everything you need to know about using systems of equations to solve single equations. You can learn more about systems of equations in Mr. Dorey's Algebra Handbook, available at www.doreypublications.com.